Um, Ross is a research scientist at Facebook AI Research, working on computer vision and machine learning. He received a PhD in computer science from the University of Chicago in 2012. Prior to joining FAIR, Ross was a researcher at Microsoft Research Redmond and a postdoc at the University of California, Berkeley. His research interests include instant-level object understanding and visual reasoning challenges that combine natural language processing with computer vision. He received the 2017 Abami Young Researcher Award and is well known for developing different models like the RCNN, Fast RCNN, Mass RCNN, and particularly in 2017, Ross received the MAR Prize at ICCV for Mass RCNN. So here, welcome and thank you, Ross, for accepting our invitation to give a talk. Yeah, you can take it from there, Ross.
All right, yeah, thanks for the very kind introduction. And also thanks for inviting me to this workshop. So I think that this is going to be a fun opportunity for me to share some thoughts that I've had recently about the workshop topic. And in particular, this is going to be kind of a bit more of a high level or philosophical talk than I usually give. It's actually not going to draw on any particular recent publications or really show anything in terms of results. But I want to use it as an opportunity to both provide a little bit of historical perspective, but more importantly, my sense of where I think our field is heading, or rather where my personal opinion about where I think it should be heading. So this talk is going to be about what I call the decoupling of recognition and grouping. And for that title to make sense, let's go ahead and dive into it. So some of you might have seen this back in 2013 or so. Jitendra Malik was going around and giving this very interesting series of talks about what he called the 3 R's of computer vision. So this was before deep learning kind of swept through computer vision. Okay, so what are these 3 R's? So one of them, the first is recognition. The second is reconstruction. And the third is reorganization. Now, recognition and reconstruction probably sound familiar to most of you with a computer vision background. Reorganization might sound a little unfamiliar, but you can just think of it as a synonym for segmentation, or the term that I personally prefer grouping. And this is, of course, modeled after the classic 3 R's in education, reading, writing, and arithmetic. And only one of those actually starts with an R. So I think that we can all forgive Jitendra for sort of coercing this last one into beginning with an R. Okay, so let's remind ourselves of what these 3 R's of computer vision look like in more detail. Okay, so starting with recognition. The classic example that I'm going to use throughout the talk is object detection. And so of course, recognition is about attaching semantic labels, sort of the concepts that humans construct, attaching those to the pixels. So in object detection, it would look like something like putting a box around an object from a pre-specified set of categories and attaching the correct labels like person or bus. And so in 2015, this is what the output of an object detection system might have looked like. So reconstruction is about attaching properties of the physical world that's out there before the picture was taken back to the pixels in the images that were captured. So a good example of this is something like multi-view stereo, which is about reconstructing the 3D shape or geometry of things outside in the world based on having multiple photos of that object or scene taken from different viewpoints. So here's an example of some landmarks being reconstructed using the CoalMap software. And now reorganization, which again is just a synonym for segmentation, or the term I like, grouping, is about taking the pixels and breaking them off of the regular grid that they're typically on, that doesn't really encode any useful information about how those pixels really relate to each other, and reorganizing them into groups or segments that for some reason belong to each other. And so that reason can be different in different cases. So for example, it might be that those pixels move together in a video, or it might be that those pixels belong to the same part of an object, or to the same object, or to the same sort of stuff, like if they're pixels in grass. So when recognition is thought about independently from when reorganization is thought about independently from recognition, the classic example of this would be something like bottom-up grouping. And in bottom-up grouping, low-level cues like edges and colors and textures are used to help bring those pixels together into groups. And this can become very sophisticated. So for example, the work that was done in Jitendra's group over the course of about a decade and a half, resulted in more and more sophisticated bottom-up grouping methods that computed things like probability of boundary, and then used techniques like spectral clustering, oriented watershed transform, ultrametric contour maps, and all these things in order to figure out how to try to bottom-up group these pixels into parts of objects and objects. So Jitendra's thesis in this talk was essentially that these three areas in computer vision shouldn't be isolated silos. And instead, we should be thinking about the connections running between them, which are depicted by the arrows here. And I think that, so this was back in 2013. I think that broadly this observation was correct, and it was a very good forecast for where things should go at that time. And as I mentioned, this was just before deep learning was about to sweep through computer vision. And so even though Jitendra wasn't thinking about deep learning at that time, I think deep learning really kind of came in and provided the toolbox that made it really easy to implement a lot of these arrows and bring these different areas together so that they would no longer be isolated. Okay, so in the rest of the talk, I'm going to just focus on two of these, recognition and reorganization. And I'm going to look at sort of where we came from when they were separated, what we've done in order to bring them together, and then my perspective on where we should go from there. Okay, so where did we come from? All right, okay, so before 2014, before deep learning swept through computer vision, recognition and reorganization were really, really disconnected from each other. They were completely separate research silos. So I'll go through some examples of this. Okay, so here's an example of recognition without reorganization. This is the Dalal and Triggs sliding window object detector from 2015. It worked on a feature map, a multi-scale representation of the image where the pixels are converted into these histogramic-oriented gradient features. And the detector was this template of weights trained by an SVM. And it would just slide along in scale space looking for the features that match the template. And this is an example where the detector, its spatial extent, the degree to which it tries to group pixels into, in this case, it's a person, is really completely independent of the pixel information. This rectangle is fixed. It doesn't change based on the input data. Of course, where it detects the object change is based on the input data, but the spatial extent, the grouping, doesn't change based on the pixel data. Okay, so now let's look in the opposite direction at reorganization without recognition. So here's an example of a system that I particularly liked back in this time. And this is the selective search method. And this effectively worked by first using some engineered features based on edges and colors and textures to perform an over-segmentation of the image. And then there was a hierarchical grouping process that merged together the most similar regions in a greedy fashion in order to construct a hierarchy. And then the union of every single segment in this hierarchy was sort of taken as a potential hypothesis for where an object might be located. And now, back in this time, to the extent that recognition and reorganization were sort of interacting with each other, it was through what I'll call a multi-system pipeline metasystem. And I've chosen this term to be intentionally very awkward and clunky because I think that kind of accurately reflects the fact that at that time, the systems we were building really felt awkward and clunky. So for example, if one wanted to do those two tasks that I was showing before, object detection with bottom-up grouping via selective search, what that would look like is first you'd have system one, which used some set of features, graph merging algorithm, hierarchical clustering algorithm, to produce some hypotheses of where objects were located. And then that information would be passed over to system two, which was itself based on its own separate set of features like hog features, SIFT, bag of words, Fisher vectors, if anyone remembers what those were. And then they were used in a nonlinear SVM in order to train a classifier that would classify these regions. So if we look at another example, semantic segmentation, which I guess I hadn't introduced as a task, but most people will be familiar that this is the task of attaching a semantic label to every pixel in the image. If you kind of came up in the deep learning era, learning about computer vision, it will probably seem really bizarre to learn that back in the day, the way that semantic segmentation was actually performed was not by labeling pixels, but it was actually first by creating a big set of bottom-up regions that were potentially overlapping with each other and redundant, and doing that with a method that didn't involve any recognition. So one of these complete bottom-up approaches like I showed earlier. And then using some kind of fairly complex secondary system that would classify these overlapping segments and then figure out how to resolve which pixel, if it belonged to multiple segments, actually, what label it should actually have in order to project back down to the output of semantic segmentation. So this was a very clunky approach, but it was by far and away at that time the thing that worked best. Okay, so one claim that I'll make is that one of the most remarkable things about deep learning as a toolbox isn't the performance improvements that it's brought. And of course, those have been vast and kind of astounding. But the other really remarkable thing is the degree to which it made it really easy and natural to couple these different parts of computer vision together. And this is something that I'll refer to as tightly coupled interaction between these different areas. So this is what I think kind of characterized the era from 2014 to the present. So continuing with object detection as our running example, I'll give an example of what I mean by tight coupling, and I'll kind of show it in a series of evolutionary stages that makes the coupling tighter and tighter. Okay, so let's start with RCNN and fast RCNN. Okay, so here you have a system which really is operating still in that kind of multi-system pipeline meta-system approach, where the input image first goes to selective search, and selective search is going to say where the objects might be. And then the thing that RCNN and fast RCNN brought was that the second part of the system would no longer be based on engineered features and SVMs, but would be sort of upgraded into, at least with fast RCNN, a more standard deep learning framework that would be recognizable today. Now, the next step in this progression was of course, faster RCNN. And this is, I think, actually where the big breakthrough really comes, because this is where the purely bottom-up grouping component of selective search was replaced with something that we call region proposal network. And this is where completely separate, isolated bottom-up grouping is really removed from the picture. And now the grouping mechanism, as crude as it is, because it's just grouping things by predicting boxes, is really part of this overall learned system. And in particular, the training signal for the grouping mechanism has essentially two parts to it. One is a loss that says how to localize things. So that part has a flavor of grouping to it. But the second is a loss that says, classify whether this thing that you're grouping belongs to any of the, say, in COCO 80 categories, or whether it's actually the background, not one of those 80 categories. And that's a recognition signal. That's not purely grouping. So this I think kind of shows where this coupling is starting to happen. You have something that's operating as a grouping mechanism, but is being trained jointly with grouping information and recognition information together at the same time. And it's also worth noting that this is no longer this kind of clunky multi-system pipelined approach. It's finally one network that's being trained end to end. And of course, this can be extended to, say, mask-RCNN, where the interactions become even more entangled and tightly coupled, because first there's this grouping mechanism with the region proposal network, and then there's recognizing it as an object. And then once that object has been recognized, there's a class-specific grouping stage, which is this mask head, which predicts the foreground-background segmentation. Okay, so we can also look at the example of semantic segmentation. So I had introduced this a moment ago and showing how it used to be done by first doing bottom-up proposals and then classifying them and figuring out how to resolve overlapping predictions at pixels. So this actually became tightly coupled with recognition extremely quickly when deep learning swept through computer vision. And I think this is a really interesting example because essentially the bottom-up grouping aspect of semantic segmentation, which was the bread and butter of methods, was completely thrown away. And grouping was essentially equated with recognition. The only thing that defines the groups in this fully convolutional or FCN approach for semantic segmentation is the category label that's assigned to each pixel. So grouping with this approach is so tightly coupled with recognition that they've become one and the same. Okay, so not only, I guess one other thing to mention is that also made the system overall very simple compared to things that were used in the past. But so not only did this tight coupling make the overall design of these approaches more regular and sort of simpler in some ways, but it also led to some pretty insane improvements in accuracy. So I used to track this on COCO and update these slides. But eventually I decided to kind of stop updating them in 2018. But if we look at the snapshot, we see that before deep learning, the results on COCO would have been about 5% AP. The first kind of wave brought that up by about 3x to 15, marching along about 3 or 4 years to late 2018. That's again tripled up to 49%, which is pretty incredible. And as I said, I stopped updating these slides, but if you look today, the best results are around 60 AP. So the march continues and the results continue to get better and better. Okay, so far I've demonstrated that there's been a huge amount of progress brought by deep learning and the tight coupling of recognition and grouping. But I want to kind of like throw a curveball because everything I've been saying is that this is amazing and great, and maybe that's like the solution, and we just need to keep pushing on that. But actually, I think that maybe this is an overcorrection. Before we were headed in the direction of these multi-system pipeline metasystem mess, and then we turned hard to the right in favor of these beautiful end-to-end networks where everything is put together in this tightly coupled fashion. But I think that it's worth reflecting on what are we losing by doing this? And if we think we're losing something, maybe it's an opportunity to try to find a slightly different path to escape the local optimum that we're potentially currently in. So let's look at sort of a more sobering picture of where we're at today. Okay, so here's some frames from a video. Here's the first frame, and we'll run mask-RCNN on it. So on this frame, everything looks great. It's finding the objects and segmenting them. Now at the next time step, suddenly we've lost the car and we've lost the truck that were just detected. That's because this car is about to get involved in an accident, and now it's flipping over onto its side. It's in some unusual pose. The region proposal network has failed to group it, potentially because it was trained with this recognition signal, and it suddenly can't recognize the object. It's clearly still an object. Its pixels still belong together, but the RPN can't find it anymore. And once it's failed, there's no chance to recognize it because it's sort of a link in this chain that's broken. So this kind of raises this issue that the models that we're building in this tightly coupled fashion can only see what they can recognize. Maybe the system will fail to recognize that it's a car because of the unusual pose, but at least we should hope that it will still group those pixels together, have some representation of it, and say there's an object there. It shouldn't completely fail at both recognition and grouping. So basically, we can only segment or localize or group the things that can be named. So a current system trained on a typical data set faced with this picture basically just wouldn't output anything. It doesn't recognize what this animal is, therefore it doesn't exist. And I think that this is now sort of where I'm connecting the talk more to the theme of the workshop. And I think that this current paradigm that we're in, where things are so tightly coupled that recognition and kind of having systems that can see objects and images are so tightly coupled, it is a very unsatisfying state to be in, and one that I think that we need to figure out techniques to move away from. So current models are also very brittle. So you can find tons of examples of this where a box is put around an object and then the grouping fails because actually there's more than one person or there's more than one object in that box. So here's another example of where that happens. So we really want systems that are less brittle. We really want systems that are less limited. We want them to be able to see things that are there even if they can't necessarily recognize them. But how can we do this? Okay, so I'm going to point to a direction that I think is one plausible way to escape from the current situation. And I'm going to do it by looking at a very concrete downside of this tight coupling. So the issue is that when you do tight coupling, there's this strong expectation that all data is going to be annotated with all output types of the system. So let's take instance segmentation as an example. Each object in the data set is expected to be labeled with a segmentation mask and a category label. This is an extremely limiting way to train systems, though, because, you can just ask yourself, if you're going to train a grouping model, what's the data that you would ideally want to train it on? Or conversely, if you were to train a recognition model, what's the data that you would ideally train that on? So my personal answer is that using a data set like Coco or Elvis isn't the answer to those questions. They're not all we could hope for to ideally train these systems. We should definitely be dreaming bigger than this. So what might the ideal data for a grouping model look like? Well, first of all, we could take all of the segmented objects in all the data sets that already exist. That would be fine. Why should we limit ourselves to just the things that are labeled with the categories in any particular data set? But also, if we had somehow access to a data set that had segmented objects, even if they didn't have any names associated with them, because maybe it's easier to collect data that way, well, that would also be great data to have. And I think that we should use such objects. So for example, one might be able to use the data in UVO as a source like this. And then of course, there are other modalities like video. So there are lots of additional interesting cues that come from the fact that you have moving pixels that might enable you to start to train grouping models using signals other than hand annotated segmentation masks. So we should be making use of that as well. Now we can do the same sort of analysis for recognition models. Okay, well, so there's more to life than the 80 categories in Coco or the 1200 in Elvis. And I think what we're starting to see now is that there's a lot of power. There's a huge amount of information for recognition that can be found in these massive scale data sets that pair images and some weakly associated text together. So in research that we've done in our group, we've seen this before with training models to predict Instagram hashtags. More recently, systems like Clip and Align show that this also works really well if you have web scraped data. So now I'll kind of put forward a toy view of an architecture that one might be able to use with all of these diverse sources of data. So here's a hypothetical sketch of a high-level architecture. So it might contain something that you'd call the grouping module. And this is going to have, or compute what I'll call the localized stream. And this will produce features at every location and scale that you want to discretize. And it will have a pixel-wise output. So this could be like an embedding vector at every pixel that can be used to say what pixels belong together. Now the system is going to have a recognition module, and this is going to be sort of another stream that I'll call the object stream. And this is going to be concerned with outputting stuff like semantic category labels, attributes, or other kind of object level information that a recognition system might be interested in, such as like parts and subparts and so on. And then there has to be a way to integrate both of these streams. So this is kind of like a what stream, and this is a where stream, using that terminology. And they should have interactions between each other. So for example, the localization stream should be able to provide information about where potential objects are to the object stream. And the object stream, based on what it thinks it's recognizing, should be able to provide information back to the localized stream that acts as some kind of priming that suggests how pixels might be grouped together based on the things that are actually in the image. And then of course one could like get fancier. I don't really want to talk about it, but like you could add something in that deals with interactions between different objects that are being recognized. So I think that this kind of direction, which I like to call the loose coupling of recognition and reorganization, is one potential view of where things should be going in the future. Because I think that it has a lot of advantages. So for example, how might you go about training this sort of hypothetical architecture? Well, you can pre-train it for grouping using whatever data. The data doesn't have to have any recognition information in it. And that can act as a powerful pre-training approach for the localized stream. Likewise, you can pre-train the recognition stream using whatever paired image and text data you have. It doesn't have to have any grouping information. Because of the loose coupling, we're no longer required that everything is labeled with everything. Then you figure out a way to nicely integrate these models, and then you can jointly fine-tune them for a downstream task, whether that be like Coco or Elvis, 820K, so on. Okay, so now I'll try to wrap this up in a minute by making a couple predictions about where I think things might be going in the next few years. So the first prediction is that I think that loose coupling will enable us to finally build much more robust general purpose grouping models. And these are going to make use of self-weak, strong supervision and video in order to train the grouping. But of course, grouping itself is very ill-posed and under-constrained. So there needs to be some kind of fine-tuning on a downstream task to actually make sure those groups correspond to something that we actually want at the end of the day. And I think that this paradigm will finally allow us to break away from or greatly minimize these kinds of silly errors that I was showing before where you have multiple objects interfering with each other over or under segmentation type errors. But these models on their own won't be able to name models, although they'll be able to see things they can't name. So then the second prediction is that loose coupling will enable the naming of tens of thousands of things. And this will be brought about by using these massive paired data sets. And we'll be able to observe interesting properties like zero-shot transfer between the pre-training and unseen data and new unseen data sets. So with that, ending just on time, maybe there's time for a question or so. But thanks for your attention.
Yeah, thank you very much. It's great talk and nice. I like the trivia and the observation of the lab, like before deep learning and thing. So let me see if you have we have any question on the question. Not yet. Okay, so I think that seems all connected. So so then you mentioned about the video thing of it, right? What do you think like the best? I mean, maybe best opportunity for video self-supervised in this domain, let's say in the motion self-supervision, or what kind of thing like wheel motion will help do the reorganization thing easier, or and then how it maybe you already mentioned, but maybe just like
so I really like this recent paper from Alan Jabri and Alyosha Afros's group, which is basically using these video palindromes. So you have some time step to time step plus k, and then from time step k back to the first time step, which allows you to know the ground truth flow that you have the pixel going from its starting point to some unknown location in the middle, then back to its starting point. And then you can use that to kind of marginalize over the potential paths that things are taking in order to train a system that kind of tracks patches in some sense and learns a representation that's good for doing that. I think that's that kind of thing, like, of course I don't have like a concrete answer to the question in terms of like what's going to be the ultimate solution, but that kind of approach I think is very interesting, and I like to point out that work.
I see. Yeah, we have like two questions on the Q&A. I think one question maybe they asked about the name of the paper that you mentioned about Alyosha.
I would have to look it up quickly.
It seemed like you mentioned about like time cycle consistency using random walk or something from New York.
Yeah, that sounds like it's okay. So it's called space-time correspondence as a contrastive random walk.
Okay. Yeah. Okay. So, and then another question is asking if segmentation can or grouping can help to solve occlusion or occlusion detection problem.
I would hope so. So as one concrete example of that, actually I didn't mention this in the slides, but so nowadays sensors in phones are either able to directly capture depth information, or they're capturing multiple pictures and the phone is doing some kind of depth estimation within it. So more and more in the future, we're going to have paired RGB and depth data, which provides another cue for training grouping. And I think that this cue is going to be particularly helpful for dealing with things like occlusion. So you could train models using this as like an extra bit of supervisory information that helps the grouping detect occlusion boundaries more properly. And again, you can only do this if you're decoupling, if you're loosely coupling things, because like this data is not going to have any recognition labels assigned to it.
Okay, great. Again, thank a lot, Ross, for giving a very nice talk. And yeah, thank you.
All right, yeah, thank you. This was fun. Bye.
Okay, great. So do we have the next speaker live up? Oh, we have here.
Hey.
Hi, bro.
Yeah, I'm here.
Can you try to share your slide or something?
Yeah, let me do that.
Okay.
Are you seeing this?
Yes. So next we have Ru Jaegle from DeepMind present here his work on perceiver I/O. Okay, you can take it from here.
Thanks, Stu, and thanks to the organizers for having me. So I'm going to be talking about recent work that I've done with collaborators at DeepMind on developing general purpose architectures, Perceiver and the follow-up work, Perceiver I/O. So basically, the motivation for this work is to try to develop architectures that can be used pretty generically on data modalities that go beyond sort of the traditional ones that we've been very good at developing architectures for. And so if we think about developing architectures as the process of basically inductive bias engineering, this has worked really well on some domains where we have good intuition. So images are of course, the golden case for this. But it's challenging to see how we're going to scale this to every possible modality that we want to handle. And this applies both to sort of traditional perceptual sense modalities like the ones shown here, so ranging from proprioception to text processing to touch. But it also extends to sort of more exotic sensory modalities, like the kind that we face in general scientific reasoning. And we basically, as a field, the argument here is that we can't afford to hand design an inductive bias to handle each of these. And so rather than doing that, what we want to do is build architectures that can sort of handle all of them out of the box. And to do this, we're going to be starting with transformers. And the reason why transformers are a good place to start here is that they have a general purpose inductive bias. So in particular, their processing is non-local. And an important property of non-local processing, so sort of all-to-all processing, is that you decouple the range of interaction, so how far points can be before they interact, from the network depth. So in convnets, you can eventually sort of compare all points, but it takes a long time till you get there. Another important property of these models is that position, so position in space or in some abstract feature space, is a feature rather than a hard constraint of the architecture. So you can learn to sort of relate things that are close by or far apart in whatever space that you're talking about, rather than have it dictated to you by your architecture. And then finally, they're very well suited for TPUs and GPUs and other accelerators, and they use extensive weight sharing, which makes them rather efficient to learn in terms of the number of parameters that they have. But of course, there are downsides. In particular, they have poor compute and memory scaling. So in addition to the well-known quadratic scaling property of transformers, which gets worse as you scale in depth, there's also just a linear scaling property, which ends up adding a lot of memory for very, very deep architectures. So transformers keep the same depth. The feature map has the same depth throughout the network. And this means you're tied to whatever your input size is, even linearly. And this is often not emphasized, but it can be a big problem for large models. To sort of show you how we're going to get around this, I'm going to walk you through what standard QKV attention looks like in self-attention, and then show you what we do to sort of mitigate both of these problems. So in self-attention, we basically take an input array, we project it with QK and B linear layers to get the output, the input to our attention here. So this is going to be a 1D convolution, and it's big O of M, where M is the number of input points. This is going to be bad because M is quite large, even on relatively small images. Like ImageNet, we have 50,000 input points. Okay, so once we have our Q and K, we then compute a matrix multiplication. This is going to be quadratic in the input size. And then finally, to get the output features, we compute another matrix multiply. This is again quadratic. So to get around this, what we're going to do is replace self-attention with a cross-attention right at the very first layer. And the way that we do this is by introducing an auxiliary latent array, which is n by d, where both of these are these are hyperparameters, and n is going to be the relevant number for self-attention. We use quite small values here to make this very scalable. So at the very first layer, we've already gotten rid of one of our big O of M operations. At the matrix multiply stage, we're now instead of having something that's quadratic in the input, we have something that's linear. And this holds for the output as well. So the final matrix multiply is also linear as well. So just to summarize this, by introducing this latent array, we've produced an attention operation that's now linear instead of quadratic in the input size. And maybe more importantly, we're producing an output array that's smaller than the image. And because this thing has a size that we can control, we've introduced a bottleneck, and we can use this to build very, very deep networks. So basically what we're going to be doing is using this to compress down to a relatively small size and then stacking very deep transformers on this. but we have control over the size, so we still get very flexible compute, but we haven't made it into domain assumptions, and we've gotten rid of that quadratic scaling. So the final architecture we have looks like this, and I'm going to be presenting sort of the perceiver I/O version of this. The perceiver itself is very similar, and I'd refer you to the papers if you're interested in the differences between the two. So the perceiver I/O takes an input array, it maps it via a cross-attention to a latent array. In this first latent array, sort of on the very far left, behaves basically like a learned initial state in an RNN. So it's sort of like weights, and they interact with this network to project it down to a smaller fixed size. We then processed this with a very deep transformer stack. And this is, again, this has linear complexity, and it's also independent of the input and output size. So we can make this very, very intensive and have a lot of compute here. Then finally, to decode from this, we use this cross-attention trick in reverse. So now we use queries, which have the size of whatever output we want. So this can be an array of pixels, it can be one classification class, it can be a bunch of different things. And this allows us to basically get linear complexity in the output size, decouple it from the input, and get outputs that we can use for many, many different kinds of tasks. So in the two papers, we show things on classification, regression, dense tasks like optical flow estimation, multimodal autoencoding, and multitask settings as well. So I'm just going to walk you through now what some of the results look like. So we can try this on standard ImageNet classification. And if we compare it against a couple of sort of standard methods that use 2D convolutions of one kind or another, we see that perceiver I/O does quite comparably, while doing much, much better than a transformer, which we sort of have to downsample the image size to make this fit. One of the cool things about this, though, is that because this architecture isn't relying on the 2D structure architecturally, we can permute the input images, and by design, the perceiver and the transformer will have no performance regression, but architectures that do sort of rely on the 2D structure in the architecture exhibit a performance degradation. And I'm not sure why you would be interested in a permuted ImageNet per se, but this gives us a sense of how well it will work on sort of more generic things where this grid structure doesn't work. As another neat sort of thing, we can basically use position encodings here that know absolutely nothing about the 2D structure of the image, and we still get quite good performances. So this is a model that's trained with literally no input information about the 2D structure, but we still see that it's getting quite reasonable classification performances on ImageNet. We also want to use this on more general domains than just images. And to be able to do this, we want to give the model some way to reason about different modalities. So the way that we do this is we take input points that come from, for example, video and audio, and we note that they have different feature dimensions and they have different semantics. So to combine them, we introduce basically a new type of position encoding that gives the model information about what modality each input point is drawn from. And we can do this for both input or output points. So basically, we have a learned embedding, and the embedding is per modality. We can use this to construct arrays that are uniform, even though they come from very different modality sources, and then pass them all to the network where they can be treated uniformly. So using a strategy like this, so position information that comes from multiple modalities that are sort of standardized with these additional features, we can apply the architecture to audio set classification. And so audio set is a large ImageNet-like multi-labeled classification data set that includes video and audio. And so we can compare how perceiver I/O, or perceiver in this case, compares to sort of standard benchmarks in the data set, or in the community. And one thing I want to highlight here is that perceiver, even using raw audio, so not using spectrograms or any other sort of featurization, does comparably to other architectures which use a whole ton of other pre-processing tricks. So this attention AV fusion, for example, trains separate audio and video networks before trains them separately, then learns a joint sort of fusion architecture to sort of reason about them. Perceiver can handle all of this just by concatenating all the features and learning to reason between them. So this suggests this architecture really can learn very flexibly over many different kinds of modalities. We can also try this on dense tasks. So if we look at Kinetics 700, we can do multimodal autoencoding here. So this is what the input looks like.
Start at the outer corner, I swirl, and I move in, and then I move back out. And you keep doing this until...
And this is a reconstruction where we're decoding all 800,000 points of the video, the audio, and the class label from a latent that's about 512 long. So
out of the other corner, I swivel and I move in, and then I move back out. And you keep doing this.
And so you can see it's not perfectly, it's not capturing all of the details here, but it's certainly capturing all of the gist. And this is despite the fact that we're giving the model essentially no knowledge about which points are from which. So it's just sort of taking all the video, the audio, and the class label together, mixing them up, and then decoding from that using a query system that knows the modality. And importantly here, the class is masked out. So this is effectively this acts as a classification network in this sort of setting. We can also try it on visual tasks that involve that are traditionally thought of as involving correspondence reasoning over large regions of space, including optical flow. And so optical flow, of course, is the problem of estimating the motion of each pixel in an image given two pairs of two video frames that come side by side. And so if we, I think one, it's useful to sort of see what previous state-of-the-art methods do, just to see how people typically think about the reasoning that's required to do this. So Raft, which won the ICCV Best Paper Award last year, builds an architectural specialization for 40 correlation volumes at multiple scales. It involves local neighborhood gather operations, as well as specialized update blocks that are used to sort of refine the local estimates that are made, and a newly introduced upsampling operator. In contrast, we take Perceiver IO, so the same architecture that we used on these other tasks. We take the input frames, concatenate them, and just pass them in. So using this approach, we find that we can get endpoint errors that are better than all of the state-of-the-art results on Centel, and that are comparable on Kitty, but we're using an architecture that has dramatically less domain information. So this model is trained with the exact same pre-training sort of autoflow and then Centel evaluation as Raft is using, but it still is but it's basically outperforming it, even though it's using a simple architecture. One of the nice things about this architecture is because we can decode at the single point level rather than using convolutional upsampling to get the output. We see that on real-world optical flow, such as this particular one, we can recover very fine details. So if you notice them, you can see the individual droplets of the water reflected in the optical flow, which suggests the model is able to track and reconstruct these with quite high fidelity. So just to conclude, our goal here is basically to build more general computer perception models, and we think this is a good direction to think about it. So perceivers are an architecture that scale very gracefully, but also have the generality of transformers. They're the first model that we know of to perform comparably to ResNets with no 2D convolutions in their architecture. They're a unified architecture that can be used for many different kinds of modalities of different scales. And the architecture as a whole is quite flexible, so it's gotten state-of-the-art on several different domains. And check out the papers if you're interested in more. We have results on language, as well as StarCraft and a few other domains. So this work was done by a great group of people at DeepMind, and check out the papers and feel free to reach out if you have any questions about this. Thank you, and I'm happy to take questions if we have time.
Yeah, great. Thanks very much, Ru, for the nice talk. So let's see if the audience has any question here. Okay, so I think we don't have this one. So what is like the next immediately future work for this direction according to your group of collaborator?
So because this is a sort of because you're talking about detection and segmentation here, this is one of the things that we're currently pursuing. So I think there are a lot of nice opportunities for this, both in single images and videos, and then ultimately we're interested in these sorts of approaches, sort of beyond sort of traditional domains as well. So I'd love to keep working on things like segmentation and clustering in non-visual areas where we can sort of use what insight we've gained from the vision community, but sort of extend it to many other different kinds of domains.
I see. Got it. Yeah, it seems like this one do well in recognition, and then the next step is I'm just trying to relate it to the 3R triangle that Jitendra and Rod talked earlier. So basically, you do well at recognition, right? And the next step you want to move to the segmentation, which is reorganization. But how about the reconstruction? I mean, let's say, do you think that it also works for some kind of like generative task or generation or content creation?
Yeah, so we definitely have some preliminary results that suggest there's no problem with using it for those sorts of settings. One of the sort of conceptual things that's strange about these models is that the latent space doesn't have any sort of 2D structure. So that's basically all thrown out at the input. It can learn it, I guess, in principle, but it's not given those inductive biases. And a lot of our intuitions, for example, for generative models are about having sort of spatially localized latents or spatially localized receptive fields that are then sort of used in the generative process. But what we've seen so far suggests that this will work. And the fact that it works on something like optical flow, which does involve sort of long-scale hierarchical reasoning, suggests that things like rearrangement are certainly well in scope for this kind of model.
Okay, great. Thank you again, Drew, for giving us a nice talk. Yeah, thank you. So,
thank you.
Yeah, thanks. Let us look at the next speaker if they already live here. Oh, yeah, we have here. So, hey, Drew, can you try to share your slide?
Excuse me?
Yeah. Can you try to share your slide? Like,
yes.
Are you able to do that? Okay, great.
We'll share the screen just one moment.
Yeah. So the next we have Hudson to present her work on GQA. So you can take it from here.
All right. Have one. Just a moment. Okay. Hi everyone, my name is Ru. I'm a PhD student at Stanford University, and today I would like to talk with you about a GQA dataset for visual reasoning and compositional question answering over real-world images. For those of you who may be less familiar with it, visual question answering is a fascinating area that interleaves together vision, language, and machine learning for a challenging but straightforward task. Given some image and some question about it, the goal is to provide an answer. GQA has a variety of potential applications. It can help us interact more intuitively and effectively with vast amounts of visual and unstructured data that are readily available to us through the web. It can enhance human-robot interaction in exploratory or emergency cases. It can help analysts in reviewing surveillance data, or may even help the visually impaired in their daily lives. And finally, from research perspective, it allows us to test our AI capabilities in a rich and interpretive manner. There has been a lot of progress in recent years on many different aspects of visual scene understanding, as you probably saw today, necessary for VQA. And so indeed, current visual recognition models have no problem at all to recognize the various objects in the image here, such as the dog, the couch, or the person. But when we people look at the image, we see much more than that. We're able to see not just independent objects, but also the full context, even a story. Not only can we tell that the couch here is torn up, but we can also infer that the dog has probably done that. We can see the look of guilt on his face. We can further see that the person is not very happy about it. And we can see it all immediately. And so, in contrast to machines, we are able to see things in context and understand interactions and subtle relations between objects or events. We easily make abstractions that focus not on the raw signals and statistics, but on the high-level semantic knowledge, which we then can apply to new situations and generalize. We can make inferences, fill in the details when there are gaps in the given information to make new conclusions. And overall, we are able to do not just learning, but also reasoning. However, prior datasets for VQA didn't fully test for that. So you can see a few examples of the kind of questions I include on the slide. And so you can notice here, the questions tend to be quite short and too simple. There are some questions about relations, like what is inside the cups, but they are rare. So most questions in prior datasets are not relational and definitely not compositional. One other main weakness that those datasets suffer from is that they have very strong and dominant question biases. For instance, if you ask what color is the apple, well, usually the answer is red or green, and usually cups are made of plastic or glass. And it turns out that models can take advantage of all of these statistics, and in fact, experiments shown that blind models that have no access to the image at all can answer on prior datasets more than half of the questions correctly. And this means that those datasets fail to really measure any visual understanding or fully visual understanding abilities of those models, since these models can just answer many questions by making educated guesses without even looking at the image. So motivated to solve these problems, together with Chris Manning, we introduced the GQA dataset for real-world visual reasoning and question answering. A key aspect of our datasets that contrast with prior work is that notably in GQA, everything is structured. Each image in the dataset comes with a scene graph, a symbolic representation of the semantic knowledge in the image in the form of a graph, which specifies the objects, attributes, and relations in the image scene. And each question in the dataset also comes with a structural representation, in this case, in the form of a functional program that lists the series of steps needed to be performed over the scene graph to answer the question. So let's look at the following example. We can see here again the picture of family having breakfast, and the scene graph that corresponds to the image appears on the left side of the slide. We have graphs for 100,000 such images based on a cleaner and curated version we made of the visual genome research collected area by colleagues at Stanford. And once we have these graphs, we then use them to automatically create over 22 million multi-step questions in varying degrees of compositionality, where each question basically corresponds to a path on that graph and has a matching functional program, as you can see on the right of the slide, that captures its underlying reasoning process and is grounded back in the image scene graph, in nodes in the graph that have to be tracked one after the other in order to address the question. The generation process of the questions was performed by a robust question engine that we have developed that traverses the graph and recursively translates the path from the graph into natural language phrases, which, while taking into account all the grammatical, linguistic, and syntactic aspects necessary to perform the translation process and create the questions recursively, starting from phrases and then combining them together in order to generate automatically recursive compositional questions. By using our approach, we're able to generate a variety of questions that are both linguistically rich and also semantically diverse. And they cover a variety of reasoning skills, including spatial reasoning, comparisons, logical operations, such as questions that involve and, or, not, relational reasoning, and multi-step inference. And you can see some example of these different sort of questions on the slide. We can also see here some statistics that show the different types of questions and answers, as well as the number of reasoning steps they involve. We usually limited them to be 2-3 in order to keep the question natural sounding, but we can also automatically create questions of higher degrees of compositionality. And remember that we provide for all of these questions in GQA, both the surface language form as well as the structured semantic program. Having the structured representations to complement each question offer multiple advantages. One example is the reduction of biases. As I mentioned earlier, previous GQA datasets tend to suffer from strong and dominant question biases, and model could exploit them to make educated guesses of the likely answers in order to circumvent part of the need for true scene understanding skills. And so to address this issue, we have developed for GQA an iterative balancing method based on rejection sampling that takes advantage of the semantic representation of each question in our dataset to achieve much tighter control over the conditional answer distribution in our dataset. Basically, we turn the distribution to be more uniform and with heavier tails. We can see the animation of the balancing process that we do here. And every iteration, we push the distribution from the head to the tail by rejecting some of the more common questions and questions with more common semantic reasoning in order to make the dataset overall more challenging and less biased. Another advantage of having structured representation for both the images and the questions is that we can use them to define multiple new evaluation metrics beyond the standard accuracy that has traditionally been used. For instance, we can check whether a model answers semantically equivalent questions in the same way or not. In other words, we can measure its consistency. To give an example, if we have a question such as what color is the shirt, and the model answers blue, then on another question in the dataset, is the shirt red, it should answer no. And similarly for other semantically equivalent or related questions. And so we measure whether the model indeed follows these entanglement relations and to what extent. Just a moment. Another example is the grounding metric, which shows us not only whether a model reaches the right answer, but also whether it looks at a relevant region in the image that corresponds with that answer while reasoning over the image. We can do so since each node in the scene graph is grounded back in the image, having a corresponding bounding box annotation. And so we can check, especially for attention models, whether the attention overlaps with the relevant bounding box. And so overall, these new metrics allow us to gain further insight into the model's qualitative behavior and reveal much more about the inner workings than if we just used accuracy as in prior works. The GQI dataset was also the basis for a competition in CVPR a couple of years ago, and we plan to have a new challenge this year. And if you'd like to find out more information about the dataset, I invite you to visit our website, visualreasoning.net. And I also encourage you to check out our follow-up works and more recent works. First, about the neural state machine, where we designed a model to perform sequential multimodal reasoning for tasks such as GQA. And more recently, we also introduced a new model in a different area called GANformer, or generative adversarial transformer, where we combine together GANs and bipartite transformers in order to, for the task of scene generation, in order to generate images in an efficient and expressive manner and produce realistically looking images from varied domains of indoor scenes, outdoor scenes, various objects, and so forth. That's all I have for the talk today, and thank you very much for listening.
Thank you very much, Guru, for the talk. So, is there any question from the audience? Okay, so maybe I just have one question. So, it's not particularly related to the dataset, but more like high level question. Like, do you think that like scene graph is like enough to cover most of like inference tasks for Q&A in like visual or something? For example, do you see any complicated relation in case of like what if object and like different objects have multiple relation?
So could you further?
For example, like for now, for the scene graph, right? You have object and you have relation connect between two
Yes.
vertices. Okay, but let's say if we have the perfect scene graph, then we have like a very good way to do inference. But what if we have like more complicated relationship between objects, let's say two-way or multiple way, or is there any confusion in terms of like representation and inference with the representation?
Yeah, I see. So I mean, GQA covers, we try to cover as much as possible as we could in an automatic setting of having it corresponding to paths on the graph, but indeed it can cover all sorts of reasonings. We try to also cover in the work kind of branches where we have like or like logical questions where you basically your path is like combining two subpaths, so it becomes a small tree. But even that case can cover all cases. So for instance, like if you have questions about counting or like about negations, these are harder. It's harder to express these questions in this approach. So indeed, GQA doesn't cover all sorts of reasonings, but the advantage of having this data set is that we generate the questions automatically.
Okay.
And so we don't need like cost of therkers to collect large amounts of questions. And also, because we generate them automatically, we have like strong supervision annotations for each and every of the questions, which, as we saw in the presentation, allow us to have different metrics and do make the data set more balanced. So we sacrifice some of the advantages in terms of like full coverage of all sort of reasoning, but we gain also some other advantages of having more evaluation metrics and having more balanced data.
Yeah, got it. I see. And then I see. So then where you see the most problem of like ambiguous come from? Like come from attribute question, or what kind of question that most ambiguous?
Yes. So what we do is that for every node in the scene graph, we also have the bounding box corresponds to that node on the image. So everything is kind of strongly supervised and connected, and like in the data set. And then for attention models especially, we can check whether when they answer some question, whether they really looked at the relevant region in the image. So like we see this here. Just a moment, it will move in a second. On this slide, I'm show the basically attention maps from the neural state machine model, where we can see that the model takes a question and then it kind of tracks like specific words by putting attention on specific words and on specific regions in the image, by having these masks of the objects in order to iteratively reason over both the image and the question in parallel until answering it. And we can only do it by the fact that we have all of this rich information to train these models, to train the object detector and train the segmentations in order to provide more interpretable reasoning when we have the model answering the question.
Okay, yeah, great. Thank you again, Ru, for coming to present your work today. Yeah, thank you.
Sure.
Yeah, have a good day. Yeah, so let's look at see if we have the next speaker lineup. Who's the next speakers? Yeah, Saquib, are you here?
Yes, can you hear me?
Yes, okay, yeah. Are you able to share your screen or your slides?
Yeah, just a sec.
Okay.
All right, so
Okay.
hope you see my slide now.
Yeah, so here, okay, so we have our last invited paper talk from Saquib from KIT. He talked about unsupervised action segmentation. So you can take it from here.
Yes, thanks very much, Drew, for the introduction. So hi everyone, my name is Saquib and I'm happy to talk about our recent work on unsupervised action segmentation in videos. We actually presented this at the CVPR this year, and you can of course find the paper and related material also online. So let me just quickly describe the problem. So action segmentation basically refers to inferring boundaries of semantically consistent visual concepts in videos and is an important requirement for many video understanding tasks. And I will talk about our unsupervised approach for segmentic actions in a video, which does not need to be trained. The main idea is actually to build an effective temporally weighted hierarchical clustering that can group the semantically consistent frames of the video. So if we look at the prior work on most weakly or unsupervised methods, whatever their degree of prior knowledge is, they primarily focus or mostly focus on acquiring pseudo-labels that can be used to supervise training of task-specific feature embeddings. So the goal is to learn some kind of embedding that would better separate the consistent frames in the feature space, right? And in this work, we adopt the view that action segmentation is primarily a grouping problem, and instead we focus on developing clustering methods that can effectively delineate the temporal boundaries between actions. This approach of taking a grouping-based view on the problem leads to actually quite interesting finding for action segmentation. So if we have good representation of frames, often a simple clustering, for example, with k-means of these appearance-based frame features achieves performance on par with, and in some cases even superior to, the state-of-the-art unsupervised methods that require training on the target video data. So in the context where many current unsupervised action segmentation methods use k-means as a step to generate labels for optimizing the embeddings in their different proposed setups, these results and baselines becomes very relevant. And for us, this finding actually indicates that a sufficiently discriminative visual representation of video frames can be used to group these frames into visually coherent clusters. So now in our previous work on clustering, we observed that first nearest neighbors are quite sufficient statistic to discover linking chains in the data. And this work, which was about this one nearest neighbor clustering, is called Finch. This Finch clustering thus builds a graph by linking all samples to their first neighbors, hence building a one nearest neighbor graph. The connected component of this graph partitions the data into fixed clusters, and then a recursive application of this on the obtained clusters could yield quite effective hierarchy of clusters for us. So based on this observation, we adapted this Finch for the problem of temporal video segmentation in this work. And our main intuition is to build instead a spatio-temporal graph by linking frames in a video based on their feature space proximity and taking into account also their respective positions in time. In particular, we want to have a representation that encodes both this feature space and temporal proximity, and which can mainly be achieved by using time as a modulating factor when constructing this graph. So for a video with n frames, a graph can be defined with edges describing this proximity both in time and in space. So as you see on this slide here, we construct a feature space graph by computing the frame's feature space distances, and the edges in the time space graph in the equation below represent the temporal difference between the nodes, which are frames for us. So afterwards, we can then use these to define edges, here shown as W, which are simply obtained by weighing the feature space graph edges with their respective temporal graph edges. And the final graph, which we then build, is connecting each node to its first nearest neighbor. And after which this 1NN graph's connected components would yield the first set of partition with some clusters in it. So the full algorithm is then building a hierarchy of these obtained clusters, much like we did before in the Finch clustering, which, by the way, if you are not aware of, you should take a look, because it can really scale well and can really handle large data. So maybe you will find it interesting also. So anyways, this hierarchy of obtained clusters is obtained basically in succession steps by merging the previously obtained clusters into new clusters. And at the end, then given this spatio-temporal graph, which is Gij, and the hierarchical clustering algorithm could produce a set of frames partitioning for us. So you can obviously look for more technical details on this in the paper itself. So another important aspect to look for in temporal action segmentation is getting a better segment length. In temporal video segmentation, obtaining this correct ordering of actions is quite crucial and quite challenging also. Existing methods, unsupervised methods, mostly employ expensive post-processing mechanisms. For example, Mellow models or Gaussian mixture models or Viterbi decoding to improve the length and order of their predicting action segments. In contrast, because of this temporal weighing in place, our clustering algorithm inherently produces time-consistent clusters, which kind of also is sort of limitation, which I will talk about in the last slide. But for now, this actually ensures that, for example, a sum cluster in the beginning of the video will never be merged with a cluster towards the end of the video, right? So thereby it can better preserve the length of the actions which are occurring in the video. As you see on this slide, in the example here, in contrast to other clustering baselines, the lengths and order of the actions are quite nice. So then, just quickly talking about some experiments, we basically tested this TW Finch on 5 commonly used challenging benchmarks, which have varying number of frames per video. For example, from 500 to 10,000 frames in a video. Similarly, they also reflect different number of actions in each video. And we evaluated on the setting, of the required clusters in a video based on the average number of actions in an activity, which is quite commonly used also with the other unsupervised method. So one thing which you should probably also is of interest is even this very naive baseline equal split, for example, in this setting actually yields quite interesting numbers. You see that every frame accuracy is 34%, so which is not that bad. So establishing these baselines actually, I think would also help the follow-up methods now in the action segmentation area. And in the end, I just want to conclude with some qualitative results to show, although, I mean, they are kind of cherry-picked, but still they reflect some limitations also, which I would now talk about. So first of all, these results basically are taken from two videos from the breakfast dataset on the left and the YouTube instructions video dataset on the right. And the visualization in the visualization on the right, we have set the background frames to white so that, for all methods. So, which could allow to actually see the misclassification and misordering of background frames to be more clearly seen, because this data set has about 60% of frames as background frames. So it actually shows how much other algorithms are mixing the actions with the backgrounds and so on. So on the left image from the breakfast video on this one, one can observe that the temporally weighted fringe accurately predicts the length of segments and also yields better segmentation boundaries, while the both clustering baselines cannot leverage this since they don't have this temporal information. They have noisy segments there. Similar observations can be made on the right video from YouTube instructions, where we show this qualitative segmentation result. So this video has 9 actions of varying length, basically, and they also have several interspersed background scenes, as you see with this white color. So two main limitations for this work, which are inherent to our way of unsupervised clustering approach are the first one actually is illustrated on the right figure here. It occurs when we over-segment a temporally contiguous sequence due to low visual coherence. And the second may occur when we assign frames that depict the same action to different clusters because they are temporally distant. So this could be a limitation, because, for example, if in a video picking cup occurs again somewhere here, then these two group of frames which belongs to the same actions would never be clustered together because of our temporal ordering in place. Yeah. So this is one limitation for this. Now, with this, I would stop here because I think my 10 minutes are probably over. And I would like to thank the organizers for this opportunity to share our work here, and also thanks to the audience for their patience. And of course, if you have any questions, then please let me know. Thank you very much.